Greetings. Welcome to our 37th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign.
And hello, everyone. My name is Jen Miller, and I'm the coordinator of the Fabricated Geomembrane Institute, or the FGI.
On today's episode, we are going to focus on our January 13th, 2022 webinar on behavior of textured geomembrane nonwoven geotextile interfaces. I'd like to quickly reintroduce our presenters. One of them is me, and the other is Dr. Robert H. Swan, a leading expert on geosynthetic interface testing, and who helped draft the initial ASTM test method for geosynthetic and GCL interface testing, which is now known as ASTM D5321. Rob is now at Drexel University. He's a teaching professor and associate department head for undergraduate studies, and recently completed his PhD there at Drexel University. So, Rob, thanks for joining us again.
All right, thank you, Tim. Glad to be here.
Okay, here we go. We've got a lot of questions left over from the live webinar presentation and 14 or 15 after the webinar presentation. So, here we go. First question, who manufactures the new structured geomembrane that was discussed? We don't like to mention manufacturers in the presentation or in the podcast, so it's a manufacturer in North America, actually the USA, and they manufacture structured geomembranes. Are there any commercial labs that can perform ring shear testing? Geotesting Express near Boston, Massachusetts. Number 3, the comparison between test results seems to imply that direct shear tests should not be used for design. That is correct for the large displacement strength. The peak strength looks like it's in pretty good agreement with ring shear, and if anything, it may be a little lower than ring shear for some of the reasons I mentioned. Sorry, Rob. And but the large displacement, depending on the allowable shear displacement in the shear box, it cannot reach residual. So the displacement in the shear box goes from about an inch as high as 3 inches, and that's the farthest I know about that's available in the industry. In the ring shear device, of course, we go well past 3 inches to reach the residual. So in the webinar, I gave recommendations for extrapolating or extending the large displacement strength from direct shear to a residual value for use in design for the side slopes of your facility. Next question. One concern I see with the ring shear for textured geomembranes and geotextile interfaces is it doesn't take into account the inherent machine direction bias in the materials. We have seen texturing where the points are curved in the machine direction, with the materials generally being placed with the machine direction in the direction of the failure plane. How do you overcome this with the ring shear device? We do not overcome that. So in a structured material, we would be shearing across the pattern, and thus you would sort of be getting an average of machine and cross machine direction. In a non-structured application or geomembrane, the texturing is variable in both directions, and I'm really speaking of blown film now. So that gives you an average across the machine and cross machine direction. Okay, number 5. Can you continue shearing in large displacement by reversal/repeat of testing in a direct shear box as we do in standard soil shear testing? In my opinion, the answer is no in the geosynthetic testing, because when you get to the large displacement value, let's say at 2 inches or 3 inches, if you pick up the box and move it back to the beginning, the fibers of the geotextile have been pulled out and they'll be hanging when you pick up the box and then you put it back down. So you're not re-engaging the geotextile at the same point and configuration that you were at the large displacement strength. So in general, picking up the box does not work in geosynthetics testing. And frankly, it doesn't work in soil either, because you're trying to orient those clay particles parallel to the direction of shear. So if you pick up the box and put it back at the beginning, you're not matching up the particles in the same part of the lower box as they were at the end. So it's done more in soils than it is in geosynthetics. I think it's more applicable in soils than geosynthetics, especially geotextile, non-woven geotextiles.
Yeah.
Number 6.
Can I just comment on that, Tim?
Please, Rob.
It's like taking a comb, and I'm one not to talk because I don't have any hair, but combing your hair in one direction, then combing it back against that direction, you get, that disturbance of the fibers, just like Tim was explaining. So that's why it's not a very good procedure to do for geotextile geomembrane interfaces.
Great, Rob. Thank you. You explained it better than I did. Thank you. Okay. Number 6. You only use landfills that look like Kettleman Hills tilted bowls as examples. A symmetric landfill with shallow side slope does not experience large displacement on side slopes. After Kettleman Hills, I don't see any case studies in the literature that attribute a failure to large displacement on the side slope. Why are you generalizing recommendations developed for tilted bowls to all landfills? I'm generalizing the recommendations for side slopes to all landfills. Doesn't have to be a bowl or a tilted system like Kettleman Hills. It could actually have a bowl on the bottom and side slopes, and residual is mobilized on the side slope. There are other cases besides Kettleman Hills that we have shown this is true for. However, because of litigation and confidentiality agreements, not all of them make it into the literature. So if the side slope is steeper than 6:1, 6 horizontal to 1 vertical, you need to use residual on the side slope. And we estimated 6:1 based on some stress deformation finite element analyses. And after, or flatter than 6:1, the shear displacements along the side slope are small enough that you're at large displacement, between large displacement and peak. So number 7, has anyone tested what happens to a microspike geomembrane with large displacement? That is the most common texturing that I see in use. Well, that is not the most common texturing in use. And Rob, do you want to talk to this question?
Yeah, I can talk about it. Basically, with a microspike type system, you're still going to get the rolling over of the points of the microspike. But I would think that along with that, you would end up with a little bit more combing effect of the fibers in the geotextile, either geotextile or geocomposite, occurring more than the knocking over, but you'll still see some rounding of the points in the microspike.
Right. Okay, number 8, we usually use smooth geomembrane on slopes. It works from top anchor channel or trench to another anchored trench on the end of slope. When may we see any problem about this issue? Well, that's a common design feature to prevent down drag on the side slopes, and that's called a slip layer or a slip sheet. So the upper face of the geomembrane may be smooth and the bottom face textured, and that allows the waste to settle in the front of the geomembrane and not create shear stresses and tension in the geomembrane. Also in seismic areas, that allows movement without pulling on the liner system. So that's a viable design approach. And that works out because most of well, a lot of the resistance is generated on the floor of the landfill because the normal stress is higher. And as I mentioned in the presentation, on flat portions of the landfill, you can still use peak strength. So you get two benefits on the flat portions, the higher normal stress, and you get to use the peak strength. And that's why you can have a smooth sheet on the side slope and still generate a reasonable factor of safety. Okay. Number 9, what is the reason that in the strength envelope comparison graphs in slides 26, the graphs do not start at the origin? So that graph deals with the textured geomembrane nonwoven geotextile interface. And in the graph, the upper envelope is the peak strength from ring shear with a textured geomembrane and a non-woven geotextile. So it has a cohesion or an adhesion intercept on the envelope of about 15 kPa because that's the Velcro effect that's developing between the non-woven geotextile and the textured geomembrane. So to answer your question directly, the Velcro effect between a non-woven geotextile and the textured sheet gives you a little adhesion at no normal stress. Number 10, also, could you kindly describe residual versus large displacement? It seems like these terms are used interchangeably. I agree. And that was one of the reasons I wanted to emphasize it in the webinar, is in the industry, people are using large displacement and residual interchangeably, and it's incorrect. And I hope from the webinar you saw that the difference between large displacement and residual can be 30 to 40%. So the residual is 30 to 40% lower. So you're actually over designing the side slope if you use the large displacement strength. The large displacement strength should always be reported with the level of shear displacement at which the test was stopped. So in the shear box tests I used in the webinar, the large displacement strength corresponds to 3 inches. But many shear boxes can only go 1 inch or 2 inches. Again, 3 inches is the maximum now in the industry. Okay. The second part of this question is, can you use a reversal of the large shear box? And Rob gave a great explanation of why you cannot pick up the box and bring it back to the beginning and restart the test with geosynthetics. Okay, number 11. Has your testing been done on nitrogen textured blown film geomembranes? The answer is yes. All the data I presented in the webinar is blown film geomembrane. What impact do you think there would be if structured embossed flat die produced textured geomembrane is used? So Rob, do you want to jump in on that second piece?
Sure. I sort of answered that in one of the earlier questions. We'll still see some rolling over and smoothing out of the points of the structured or embossed geomembrane, but because of the higher, I guess, the higher stiffness of those structures, especially one that is really a structured point compared to just an embossment, it's going to do a little bit more combing and reorientation of the geotextile fibers, either in the geotextile or geocomposite, but you'll still see that softening effect that was clearly shown with Tim's interface testing with the nitrogen blown geomembrane.
Hey, number 12, I assume the testing has been done at laboratory temperatures 20 degrees Celsius. The answer to that is yes, that's correct. US, probably 70 degrees Fahrenheit. What impact do you think there would be on the results if the testing was conducted at elevated temperatures, which have been recorded in landfills up to 60 degrees C? Generally, you'll see a softening of the geomembrane. There is data now available on elevated temperature shear tests, and the texturing is is softer. You do get an initial Velcro effect, but then the texturing gets smooth because now the texturing is softer, more pliable, and it can get smoothed out quicker. So we generally see a smaller or a lower residual strength with an elevated temperature geomembrane than we do with a regular temperature or room temperature. 13, what are the material property differences between old geomembrane and new geomembrane and GT on slide 47? What we were trying to convey there is we ran 3 different tests and we varied the materials. So first test is new geomembrane and new geotextile. So this is a virgin textured geomembrane and a virgin nonwoven geotextile. So that's our sort of maximum. Then after that test, we replaced the sheared geomembrane with a new geomembrane and put the old or sheared nonwoven geotextile on top of it in the ring shear device. And we can do that because the top platen comes off. We keep its orientation exactly the way it came off. We change out the geomembrane on the bottom. We put the top platen back on and then restart the test. And then we have a virgin geomembrane and a sheared nonwoven geotextile. The last combination is the sheared geomembrane is left in place and a new nonwoven geotextile is applied to the top platen and then put back on top of the sheared geomembrane or old geomembrane. So I hope that helps clarify the test results. We're working on a paper to present those results.
All right, thanks, Tim. I think this next question is directed to Rob. What does it mean when you have an internal failure within the GCL when doing the large displacement test before you reach the normal load expected from waste height at final grade?
That's a good question. What's really going to happen in your system is as you go higher in normal stress, you're going to be measuring peak, and there's very good possibility that there will be a weaker interface that fails under the higher normal stress. And it may very well be less than the peak strength of the GCL. So what will really happen is you'll slip on another interface and you'll never challenge the GCL past its peak that would cause it to fail and then develop a large displacement and then eventually a residual strength. So the high likelihood of an internal failure to GCL at high normal stress may or may not occur because of a weaker interface. And so that was what Tim was trying to bring forth when he was looking at multi-layer testing and doing the analysis of which planes were going to fail at what range of normal stress.
Great, Rob. Thanks. Number 15. When you say old geomembrane or old GT, does that mean unexposed and just aging after installation as a liner system and covered with waste? Is this material aged as if it was in place for 20, 40, 100 years? No, I tried to explain that just a minute ago. All that means is old is it had been sheared to residual in the first phase, and then one of the geosynthetics, whether it's the geomembrane or the geotextile, was swapped out for a new piece. And we were trying to use those tests to estimate what percentage of the strength loss from peak to residual is due to combing and breaking of the geotextile fibers versus polishing and smoothing of the textured surface. Number 16, how does the ring shear device work? for each degree of rotation, the displacement further away from the rotational axis experiences a higher displacement. Absolutely correct. So it's like running around the track at your local school. If you want to run a little further, run all the way in the outside lane and run around the track. You'll go further than if you take the inside lane, where I am, and run around the track, because it's a shorter distance. So there's been a lot of work on the effect of the different level of displacement at the inner portion of the ring versus the outer portion. So as long as the ratio of the inner diameter to the outer diameter is 0.5 or greater, the difference between the inner and outer radius doesn't matter. And that goes back to a 1936 PhD thesis by Vorslev. So in our ring shear device, we use a ratio of 0.5 to 0.6 between the inner and outer radii of the ring specimen. So and when we calculate displacement, we use the average radius from in the middle of the annular specimen, not the inner radius or the outer radius. So we always use the average. And that's how we plot the shear displacement, with the average radius. By the time you get to residual or even large displacement strength, the displacements are so high and the texturing and combing has progressed so far, there's really no difference between the strength or shear resistance being measured at the inner radius versus the outer radius. Now, that's all the bad news. The good news is if your ring had a ratio less than 0.5, you would actually be conservative, because the outer portion is at a higher displacement than the inner. So it's already past the peak when the inner is reaching the peak strength. So you actually get a little lower peak strength out of the ring, generally, unless if there are problems with the direct shear box. Sorry, Rob. Because you're at a different displacement. But by large displacement or residual, there's no difference.
Okay, great. Question number 17 to Rob. If the primary spikes are rolled over and the geotextile is coming parallel to the direction of movement, what will the secondary spikes have to grab onto?
That's a good question. The way the system was designed with the 2 layers of texturing is that it's a progressive movement. So not all the combing is complete once the primary texturing is rolled over. There's still enough geotextile there to get hooked into the secondary spikes and continue to develop shear resistance. Some of that is critical on the spacing, so you don't want to have too much space between your primary texture and your secondary texture, because then there really may not be anything left because of the alignment of the filaments. But careful, the work was done numerically to find an appropriate spacing to make sure that there was still enough material to help increase the large displacement and then residual strength.
Okay, thanks, Rob. Okay, we are now entering the questions submitted after the live presentation through the post-webinar survey. And there are 16 questions. So we had 17 after the webinar and 16 submitted post-webinar. Number 1, have you seen any tendency to lose the original surface pattern in the geomembrane depending on the material made? For example, PVC, polypropylene, HDPE, which one could be easier to lose the engraving after the test? So PVC and polypropylene generally have what's called a smooth or filed finish, where there's a small pattern from the roller or calendars embedded or embossed into the geomembrane. That pattern and the smooth surface remain. We've done a lot of ring shear testing on those surfaces, and they remain intact. There's a paper in the early 2000s by myself and Ryan Hillman on PVC geomembrane interface stress. I'd be happy to send it to whoever is interested. High density polyethylene and LLDPE. The focus of this webinar is sort of the polishing or smoothing that occurs to that texturing. And so there is a reduction with shear displacement for that material.
Okay, question 2. Can a step-by-step guide be created that would detail the following? 1, how to set up / conduct a single interface test, ring or box. 2, how to plot data. 3, how to apply data, large displacement and or residual. 4, how to determine maximum slope angle. 5, how to determine factor of safety. 6, how to determine where in the slope base design to apply large displacement and residual displacement tested products.
All right, well, this is another good question. There is actually an ASTM published guide. It's ASTM D7702. Now, this guide is designed for the person who may be specifying an interface direct shear test, or somebody who's got requested data and received data and needs some guidance on how to interpret it. But it's really focused more or less around the test and the test results. So there are good guidance on how the test should be specified, how it should be set up, and what to do with the data when you receive it. When it comes to how to determine the appropriate factor of safety and determine the maximum slope angle, that really falls outside of the guidelines of ASTM, since they're a test procedure agency. But I think this guide, D7702, is a very useful guide and could help you along with that process.
Okay, great. Number 3. Rob, you have shown that 2 different structure heights increase the residual strength due to the engagement unworn structure. How would an irregular asperity height affect the increase? Is there test data that compares irregular structures to the one you presented?
I think I'll answer the last question first. I'm not aware of any test data that compares irregular texturing to this new proposed dual spike system. This material is still in its, I'd say infant stage, but it's really getting close to being put out for commercial use. A lot of the work that was done mathematically and numerically to help guide the development of a couple prototypes. And I know that some prototype spacings were tested and they optimized them again. And because the cost to build a system to make these structures is very expensive, so the manufacturer wanted to only make one large production roll. And so a lot of work was done with little samples. But I don't think it's been to the point where there's been a lot of comparison data other than comparing it to what's been already tested and what's available in the literature.
Okay. Number 4, who manufactures the new geomembrane with alternating spikes? They're in the US, North America manufacturer. In the ring shear, how does one account for varying displacements of the specimen based on the distance from the center? As I described previously, we use the average radii to calculate the shear displacement, and that's done. Each degree it moves, the ring moves, you can convert that to a distance with the circumference.
Number 6, how would the polishing be impacted by a structured textured geomembrane?
Well, this is similar to an earlier question. And basically, the structured geomembrane is still going to experience some rolling of the points of the structure, but again, because of the stiffness of these structured components, there's probably going to be not as much polishing, but more of the combing of the geotextile, either the textile or geocomposite geotextile.
Okay, number 8. This is probably, I won't say that. How easy / difficult is it to apply a new geotextile to an old geomembrane without damaging the old geomembrane in the process? Is it easier to install a new geomembrane along with a new GT? So this question goes to the tests I mentioned where we are swapping out one of the geosynthetics to see how much contribution the strength loss is due to polishing of the texturing versus combing and damage to the geotextile. So it's really not hard to replace either one. The ring, the top platen of the ring is just pulled off, and then we can remove the geomembrane from the bottom platen or leave the geomembrane on the bottom platen and then take the geotextile off the top platen and replace it with a new one. So it's easier to replace one of them than replacing both and use a new geomembrane and GT for the test. So it's actually been fairly easy to start investigating the contributions of strength loss from whether it's the combing or the smoothing of the texture. Okay, number 9, can you identify the manufacturer of the 2-tiered texture product? As I mentioned, they're in North America, US company. What is the size of the ring shear specimen? Have there been investigations into size effects with ring shear testing? Our ring shear device uses an outer diameter of 4 inches or 100 millimeters and an inner diameter of 1.5 inches or 40 millimeters. So the specimen width is 2.5 inches. So there's 2.5 inches of geomembrane width shearing against 2.5 inches of nonwoven geotextile. That's the main size we have used. We've used smaller, but we like this 2.5 inch. Smaller gives the same result, but I think that's too small. I don't know of any testing with a radius greater than 4 inches. Number 11, is there any difference between ring shear and direct shear test results due to machine direction versus cross machine direction? And I mentioned this earlier before, that the ring, we're crossing from machine to cross machine direction in the ring shear device, and which that I think is okay for a blown film product. But if it's a structured, it probably has some problems unless it's a very small or micro structure. If it's a smooth sheet, like I mentioned before for PVC or polypropylene, or even a filed or a slightly embossed side, it doesn't seem to make that big of a difference between ring shear and direct shear because the texturing isn't that big either in the machine or cross machine direction.
Okay, Rob, in your prototype geomembrane, did you study the influence of the difference between the asperity heights of the primary and secondary spikes in the peak and residual shear strength values? Is there an optimum increment of height that helped to protect the secondary spikes?
Yeah, this is a good question, and we have addressed it earlier. A lot of the work that was done was through mathematical calculations and some numerical modeling to see what that influence was, not only on the spacing, but on the heights of the primary and secondary. And then a couple prototypes were made to test to see what those results were, if they confirmed what the modeling indicated. And for this particular manufacturer, they came upon an optimum increment of height to protect the secondary. And that information, I can't provide any more detail on that. other than work was done, but not as much on the actual testing side, but more on the numerical side.
Okay, number 13, why isn't the torsional shear device the industry standard? Is a direct shear test theoretically capable of directly measuring large displacement strength? I would assume not, due to the introduction of fresh material as the box moves relative to each other. Great questions. Fantastic. So I don't know why the torsional shear device hasn't become the industry standard. Rob wrote the ASTM test method D5321, so that was out first. I've written ASTM test methods for ring shear testing of soils. I have not done that for geosynthetics yet. Just hasn't come up the action item list fast enough. But I think it's a great test. It gives you peak and residual. And I agree, the large displacement strength is problematic. And one of the reasons that it is higher than the ring shear at the same displacement. So what I mean is, if you run a direct shear test to 3 inches and you go into the ring shear stress displacement curve at 3 inches, the direct shear will be higher because you are shearing virgin or fresh material as the box is pushed out over top of the new geomembrane, for example. That's called a runway. And Rob's going to jump in here any minute and get upset with me, but there's that's brand new geomembrane out in front, not sheared, whereas in the ring shear device, we are shearing the same geosynthetic continuously as you would in a slope. So I think this webinar is motivating me to start thinking again about submitting a ASTM test method for using the ring shear device for geosynthetics testing. Rob, do you want to jump in?
Yeah, and that would motivate me to put a negative on that. Stop it in its tracks so we won't go out of business. I agree with what Tim is saying. The direct shear box is a limited device, but it does give you an indication of the large displacement strength. And using Tim's proposed method, you can mathematically predict where you think the residual strengths may be. I have a little concern about the size of the sample on the torsional, on the ring shear. And prior to us getting started today, Tim asked, what if we were to make a big box? Well, you know, maybe on the size of 12 inches so that we could capture more of the geosynthetics. It goes to some of that concern that one of our guests asked about the differential between the inner radius and the outer radius. It's going to be exaggerated the wider the sample is. So I think that is one downfall of trying to make the ring shear up to scale to be similar to the direct shear. But I think they have a purpose and they've been in existence. We used to have a friendly rivalry in the 90s, but I think things have calmed down. And as a designer, you just need to be comfortable with the results you're given, whether it's a large displacement from the direct shear or a residual from the ring shear.
Yeah, Rob, let me jump in. So in going to a larger ring, I would still maintain the ratio of the inner to outer radius of a half. So I try to keep that ratio the same, so the peak would still be reasonable. However, if you went to a ratio less than 0.5, all that would do is give you a more conservative estimate of the peak strength, which is a good thing given the failures we're seeing. And we only use the peak strength on a very small portion of the facility anyways. A lot of times the side slope is the longer piece of the failure surface, so that's more important. But you do generate the most of your resistance where the high normal stress, and you can generate a peak strength on it. Second is, that was one of the objectives of this webinar, is to try to find a happy medium between the ring shear and the direct shear devices. And that was the motivation of providing listeners ways to extrapolate or extend the large displacement strength to the residual value.
Okay, next question. Rob, based on your portion of the presentation regarding short/long spikes, what manufacturers have been able to produce geomembranes with these characteristics? Is the long or short random, or is it calendared?
In this particular case, these would be a calendared structure that allow them to be having a longer primary texture and a shorter secondary texture. And just to follow back on Tim, maybe Tim and I can combine our efforts to design a larger ring shear and bring it to ASTM.
That sounds great, Rob. Yeah, let's do that. Okay, number 15. Based on my presentation, it seems most geomembranes or HDPE. Are the findings true for other materials like PVC, PVC, polypropylene reinforced geomembranes? Not really, because unless those are textured or have a significant texturing. The polypropylene, PVC, and reinforced products generally have a smooth or a filed finish from the rollers or calendars, and that finish really stays. And we saw that in our paper on PVC geomembrane interface strengths in the early 2000s. So we don't see as big of a strength loss with the other materials that we do, these blown film textured materials. Okay, last question. How do you determine the displacement, shear displacement in a ring shear device? So as I mentioned, we use the average radii from the inner to the outer, and each degree there's an equation in the ASTM D6467 or ASTM D7608 ring shear test for soils. And in there, there's an equation that converts the number of degrees you've traveled to a linear displacement, say in millimeters. And it's just a geometric calculation, because you can imagine a circle. Just imagine a clock on the wall. If you go from 12 to 1 o'clock, that hand moves that many degrees, and then that's the circumference of the circle from 12 to 1, which is calculated from the number of degrees between 12 and 1. Okay, everybody, thanks so much for all the questions. There were more than 30 between the ones during and after the webinar. Thank you so much for your interest and for attending the webinar. Thanks so much to Dr. Swan for joining us again. Rob?
Yes, I'm glad to have joined and helped with answering these great questions. And I appreciate being involved.
Great, Rob. Thanks for joining us. If you have any additional questions or would like additional information on the FGI, please send your questions to fabricatedgeomembrane, one word, @gmail.com, or you can visit the FGI website for the slides of the presentation, a recording of the webinar, and this podcast at fabricatedgeomembrane.com. Thank you, everybody.